A second source of examples is, and I've said this twice already, this is DG modules for graded algebras. Now let me postpone explaining this to the very end of the lecture, because it actually comes in, this is quite important. This example is important for the next lecture, but not so much for today. I don't want to introduce notation and explain now, so I'll explain later. On the other hand, these are just two sources. They don't exhaust the class of differential modules. There are really many more differential modules than these two. So there are many more, and just to give you one possible class of examples, so take suppose R is S in the center of the ring. So this is the center of R. So I'm not assuming R is commutative for the moment, but if it's commutative, then this is just an element. This is just the whole ring. So take any element in the center which is square 0. So take an nilpotent element of index 2 in the center of the ring R. Then for any R module M, you get a differential module where lambda R is nothing but multiplication by R. So any R module, you can enhance it to a differential module over the ring R. And you can see, for as long as R is not 0, you can see that this differential module doesn't come from a complex. For example, it need not come from a complex. For example, if M is indecomposable, it can't come from by totaling a complex like this. So I might talk of this as the totalization of the complex. Yeah? So such not arise from totalizations. Okay, so there are really many more examples of differential modules than complexes. In fact, to drive home this point, let me focus on even more specific context, where the distinction between differential modules and complexes becomes quite clear. So this is So suppose you look at a differential module D. Yeah? And suppose D is free. Say of rank n. Yeah? Then you can describe, by picking a basis for D, you can describe delta as a matrix. Yeah? After a choice of basis, so delta corresponds to a matrix an n cross n matrix over the ring R. So it's a square matrix. It's a square matrix, n by n matrix over the ring R. And the fact that delta square has to be 0 means that the matrix has to square 0. So I should say, instead of element, I should call it a matrix of square 0. So in other words, what I'm saying here is that if you look at differential module structures on the free module of rank n, they are nothing but n by n square 0 matrices, right? On the other hand, let's see what happens if you start with a complex of free modules. Let's say a complex of finite free modules, finitely generated free R modules. Right? Then let's look at I want to describe the differential of the totalization. So if you look at the totalization, then this is just Fa. So it's the direct sum of these free modules, and the corresponding differential has the shape the following shape. So I want to represent the differential by a matrix. So if I pick basis for each of these, so I pick a basis for Fa first, then Fa plus 1 all the way up to Fp. Here. So this is Fp. Now, so what you end up with is a matrix, and the point is that in this matrix, of course, it depends on how you write matrices in endomorphisms of a free module, but I want to write here the image of the vector or the basis elements coming from Fa. So the image of Fa is all 0. So here it's all 0. So this column is all 0. The image of Fa plus 1, this is Fa plus 1. It lands in Fa. So you have something here. You have some matrix here, and the rest is all 0. It has no image further down, and so on and so forth. So here it's Fa plus 2 is 0 here. The only image is in Fa plus 1, and 0, and so on. And finally, the Fb has only an image in Fb minus 1 and 0 elsewhere. So what you see here is that this is the diagonal of the matrix. So it's all 0 below on the diagonal and below it. It's also 0 beyond what's called a super diagonal. There are only blocks sitting right above the diagonal, and then it's 0, right? So it's what's called a block super diagonal matrix. So a differential module corresponds to an arbitrary square 0 matrix, whereas the differential modules coming from finite free complexes correspond to matrices of this special form, where you can write them in such a way that it has one chain of blocks right above the diagonal. So that's the difference between these two. So let me actually give you a more specific example. And this gives me also an excuse to introduce an important example in this subject, at least for this lecture.